In this chapter, you may have noticed that we're going from one section to another, and we're identifying various uses of the derivative idea and the tangent line idea specifically. Well, in this segment, we're going to do the same thing. We're developing an idea about using the tangent line to approximate the graph of a function if we're talking about a very tight neighborhood. And that's the first part of the development of a certain idea here. We're thinking this. Now here's what I said. I said, within a certain neighborhood, the tangent line approximates a function. That is, they have the same value within a certain neighborhood. If I'm talking about this graph and this tangent line at that point, then if I'm thinking about a tight enough neighborhood here, then f of x's in this neighborhood are pretty much the same as f of the x's for the tangent line. All right, that may seem a little bit confusing. It's hard to say what I mean. It is that the tangent line and the function are pretty much identical within a tight enough neighborhood. Let me show you an illustration of the situation with a practical example. If f of x is the square root of x, and our target point is 4, then let's just choose a value that's just a little different from 4. Let's just go a tenth over. So think about 4.1. So our small difference is 1/10, and f of 4 plus 1/10 is the square root of 4 and 1/10, or this value, 2.0248. Now, let's see if we can identify f of the same point on the tangent line. Now, we need the graph, we have the graph of the tangent line. We need the equation for the tangent line. So let's develop that first. The equation is given by y minus y1 equals m times x minus x1. And generally what we're doing is this, and I'm using a symbolic form here to show you where the elements within this equation for the tangent line are coming from. This is just f of 4. It comes directly from the function, all right, this y component. Now notice that we're thinking about this as the point. That's the point-slope form. And in that point-slope form, we need coordinates of a point and we need a slope. So this is the point, is the point 0.42, and we can think of this as some maybe general c value, and then f of c if we want to. It is 4 and f of 4, which is 2. Okay, that's the idea generally. So this is the f of 4. Now the slope of that line at that point is just f prime of 4, okay, and then x minus the 4. All right, symbolically, that's what it's all about. Now, we need an f prime here in order to calculate f prime of 4. So the derivative then of our function, the function, remember, was the square root of x, and it turns out that its derivative is 1 over 2, the square root of x. All right, f prime of 4 then means pop a 4 in here, and we have the square root of 4, 2. 2 times 2, 4, so this is 1/4. Now, in this place, then, we have the 1/4. That's why this is here. All right, I brought down the x minus 4, and here f of 4 is 2. So away we go, and here's the equation for the tangent line. Cleaning it up a little bit, it becomes this. Now, if this is the equation, and we want x to be 4.1, then replace this x with 4.1 and evaluate, we get 2.025. Notice that this value and this value are very similar to one another. So it's almost the same. So within that certain neighborhood, the function and the tangent line have pretty much the same behavior, same values. Okay, now let's extend the idea. Let's talk about the neighborhood a little bit. But now we want to talk about changes in x, but we want to identify this. Now, and when I say changes in x, we have a target point, like, and I'm going to call it C here. And we want to think about that change. I'm going to exaggerate the situation, and this is just a magnification maybe of what we had over there. But think about a little difference in this, this horizontal distance. We can call it a delta x if we want to. So this distance then is the delta x. And this point is C plus delta x. Now, f of C plus delta x would be that point, this vertical distance. And here's what we're after. I'm interested in calculating the change in the y here, the change in that distance, given a certain change in that distance. When we change the horizontal distance a certain amount, how much is the vertical distance changing? That's an important idea. We'll see why in just a little bit with some problems. But that's what this is all about. Now, this distance right here, from here to here, is delta x. And we can think of the distance from here to here as delta y. So we'd like to make some calculation in that regard. We'd like to know what delta y is under certain circumstances. Well, it's pretty easy for us to figure out the delta y with a particular simple function like the one that we've just been talking about. Now remember that the delta y would be the difference between this distance and that distance. So if we take f of c plus delta x, so f of c plus delta x puts us right up here. That's this distance. And then we take away this distance, which is f of c. You see, then we'll have the delta y. So delta y then is f of c plus delta x minus f of c. And for our function, it was, let's see, the c, that target point was 4, the delta x 1/10, and f of 4 plus 1/10, we found it earlier to be this. F of 4 is 2, so that delta y is 0.0248. So this delta y is the 0.0248. Now, it turns out that this calculation becomes rather cumbersome if the function is kind of messy, if it's complicated. I mean, think about it for a minute. If we're thinking about a c plus delta x and we're putting that value into some very complicated function, then this calculation becomes an adventure. And this calculation may also become an adventure if the function is particularly complicated. On the other hand, if we're talking about a tangent line, that's just a linear function, you see. So dealing with the same idea with a linear function is just easier from an algebraic standpoint than dealing with this kind of idea. And if we're talking about a close enough neighborhood, then the two values are the same, or pretty much the same. All right, let's make the calculation. Let's calculate this delta y idea, but we're thinking of it in terms of tangent line. Now I'm going to try to, let me exaggerate a little bit. All right, so it's the idea that we make the delta x, we consider the delta x, and this delta y is what we're after, and the delta y for the function and a delta y for the line are pretty much the same thing. Now I'm calling it a delta y for the line, and I'm using the same idea for the function, and they're not quite exactly the same, but let me just flow with this just a little bit. It turns out that the delta y that we were talking about for the function is approximately the same thing as, and just stay with me for this for a second, it's approximately the same as f prime of c. The slope of the tangent line at that target point times the delta x. Now there isn't any big surprise about this. I'll tell you where this comes from, and let's just digress from this for a moment, and I'll tell you how this is calculated. Now think about just the basic idea of slope. You know, the slope of a line, it is change in y over change in x. Now change in y can be thought of as delta y. Change in x can be thought of as delta x. So slope can be thought of as delta y over delta x. Well, multiply on both sides of this by delta x. These delta x's cancel. We have delta y equals slope times delta x. Now, what is this? Well, slope, you see now we're talking about a line, and it just so happens that this is the tangent line of a function. Well, this is f prime of c, and the delta x is here. So no wonder this delta y, you see, is equal to f prime of c times delta x. Okay, Now, I'm using two different delta y's here, though, and that's confusing. We're going to get away from that idea of using two different values to mean the same thing. This delta y has to do with a difference in y components on a line, and the other delta y had to deal with, or dealt with, a difference in y components having to do with the curve. And they're not quite the same thing. The one having to do with the line approximates the one having to do with the curve, but they're not exactly the same thing. We'll differentiate the two in just a little bit. Okay, so this gives validity to the idea that the delta y is approximately, this delta y over here, is approximately f prime of c times delta x. And let's see how easy that turns out to be. Well, f prime of 4, you remember our f prime function 1 over 2 the square root of x. If the x is 4, then this turns out to be, let's see, f prime of 4, 1/4, or 0.25. The delta x was 1/10, and multiplying here we get 0.025. All right, now notice and compare this with this. You see, the delta y's, these are approximately the same thing. This delta y is approximated by using this idea. Now, we need a name for this. We need to call this by some name that is other than delta y. The word that we're going to use for that other name is differential. And let's make this agreement that delta x is called the differential of x and is denoted dx. Now, dx and delta x are identical, all right, but this is differential of x. Now, for the y idea, differential of y has to do with y distance changes having to do with tangent line, whereas delta y has to do with y distance changes having to do with the curve. So that's the difference of those two, and we want to bring that up right here. The differential of y we'll denote as dy, and that's going to be equal to f prime of x dx, and that's approximately the same thing as delta y. So delta y and dy are not the same thing, but delta x and dx are exactly the same thing. That's an important idea. Now notice this relationship here has a relative, and the relative is this. Recall that if we had a function f of x and we're going to find its derivative, that there are several ways of indicating derivative. There are several notations. One of the notations is this, that we can say that given f of x, that the derivative is the derivative of y with respect to x. And that is the same thing. Another way to say that is f prime of x. Now look at this notation and look at the similarity in these two. Now let's not lose that relationship here, that gee, if we just multiply on both sides by dx, thinking of it as a value, then we would have dy equals f prime of x dx. Same thing that we have here. Now these mean entirely different things. This is the derivative of f of x, right? A different kind of thing. A function that gives us values that give the slope of tangent lines at points. Okay, fine. This has more to do with a difference in y components in the neighborhood of a certain target value for x. But the notations allow us to transition from one to the other rather easily. We'll have more to say about this in just a little bit. And incidentally, this notation for derivative, this notation right here, was chosen specifically to correlate with this idea of differential. Okay, here's how the differential idea can be helpful. Suppose we have this situation. The radius of a ball bearing is measured to be 7/10 of an inch. If the measurement is correct to within 1/100th of an inch, estimate the propagated error, I'll talk about that in a minute, the propagated error in the volume of the ball bearing. Propagated error is the error that might be indigenous to a tolerance that is of this value. A possible error, you see, is this tolerance notion. Now, so we're talking about tolerances here. How much will the volume change if we are in this range of error? You see, that's really what this is all about. How can the volume change? Well, the volume of a ball bearing is calculated as 4/3 pi r cubed because it's a sphere. The radius of the sphere is 7/10. The delta r, the difference in r that's possible is within plus or minus 1/100th of an inch. All right, now with that in mind, we're going to estimate this possible error, this propagated error in the volume. Now actually what I want to do in this problem is I want to show you the exact calculation for that change in volume and then the estimated change in volume to just show you their relationship and the nature of the two calculations. If we're going to calculate the exact error in volume, then we would need to first of all calculate the volume given that the radius is 7/10. Okay, fine. Then we want the volume if the radius is 7/10 plus or minus that 1/100th. And then take the difference in those two. That would end up being the error or the change in volume, the difference in volume. So here's that calculation. So the actual error then is found by taking I'm going to call this V1, the first volume, is the volume in terms of a radius of 7/10. And V2, I'm using a radius of 7/10 plus 1/100th. So 0.71 is the radius of this sphere. Now, performing the calculations, and it'll take several steps, but punching the calculator or whatever, we find this volume to be approximately this amount and this volume to be approximately this amount. Now, notice that I said that this is plus or minus a certain amount. That is, I'm adding the possible error here. I could have subtracted the possible error and I would get the same difference on both sides, sort of. But think about this now. All right, this volume is a little bit bigger than this one, so our delta V, our change in volume, would be V2 minus V1. All right, and we take this value and subtract that value, then delta V would be this. All right, so this is a rather exact value. I say it's rather exact, and there's an approximation built in here because this is a rounded decimal, that's a rounded decimal, and when they're subtracted, we possibly multiply that error in the calculation. So this is not an exact value to begin with. Now we can estimate this, we can approximate this using the idea of differential. Now the differential of the volume is approximately the same thing as the delta V, which we just calculated. We calculated exactly delta V over here, or more or less exactly delta V, but it's approximated by the differential of V. The differential of V is V prime of that target value for R times the delta R. And let's calculate V prime. Now, the derivative of the 4/3 pi r cubed is what we're calculating here. So it turns out to be this. And then the dV is, let's see, 4 pi, the r that we're talking about now is this 7/10, and it's squared, and then times the delta r, which is plus or minus 1/100th. And then multiplying this out, we get the dV to be this, the differential of volume to be this. Now compare this, take a look at this, and compare it with this. It's very, very close. Very, very close. And the closer we get to that with that tolerance, if that tolerance is even closer than this delta V versus the differential of V, will be even closer. Now, does this kind of differential, this kind of difference in volume, does it make any difference? Is it valuable? Is it significant? Well, let's see. We're talking about an error here, and let's say the error in some calculation is 2 inches. Certainly, if we're talking about building a road from Orlando to Atlanta, then a 2-inch difference in that entire distance would make very little difference. That's not a big deal when we're talking about such a long road. On the other hand, if we're talking about brain surgery, then 2 inches makes a huge difference. It's a very significant value. So whether we're building a birdhouse or working on the space shuttle, it will be significant according to the overall measurement involved in the problem. Well, to identify that kind of significance, we can calculate an item called relative error. The relative error is the error related to or relative to the overall measurement. So the relative error is the error that we calculate over the overall measurement. Now for our problem, it would be this differential of differential of v over the exact volume, you see, for a radius of 7/10. And that fraction turns out to be this, and as a percent, sometimes it's valuable to write this as a percent. It's a percent error here as 4.286%, which may or may not be significant, but it can be compared to the error within other problems using this percent idea. Now, symbolically, the situation runs like this. So the error is the differential of v over the volume, and if we take this idea of the symbolic form, and if we had not made the calculations earlier, look at how nice things would turn out in this form. You would need to calculate the v prime here, but this is the v prime times the delta r, delta radius, and then over v, which is 4/3 pi r cubed. Then a lot of nice cancellations occur, and we have 3 times delta r over r. So it's 3 times 1/100th over 7/10. And this then becomes what we have here. And I should put plus or minus right in here to make it exactly this. And then we get to the same place without even all of the calculations that we had here. The measurement of the side of a square is 12 inches with a possible error of 1/64th inch. Use differentials to approximate the possible propagated error in computing the area of the square. Now notice it says we're going to use differentials. We're approximating that error. We could actually figure the exact error by finding the area of the square with side 12 inches. Then find the area of a square with side 12 plus 1/64th inches. And then take the difference of those two, and that would be the exact error that we're talking about. That error can be approximated, though, using differentials like this. Now let's look at our information. The side of a square is 12 inches. The error is plus or minus 1/64th inch. Now that 1/64th inch is the delta x, which is also dx, or the differential of x. Now the form that we're using, this is kind of the template that we're using for our calculation. The differential of y is f prime of x dx. Now that's just based upon the idea of a general function y equals f of x. The differential of y takes on this form. Now we'll cause that to fit our problem. Our problem involves area. Area is x squared. So we want the differential of the area. So it's dA equals a prime dx. Now the a is x squared, so a prime is 2x. And now we can just fill in to our relationship on the left. The a prime is 2x, and the dx from above we found to be plus or minus 1/64th. The value of x is given at the top of the screen as 12 inches. So the dA, the differential of area, is plus or minus 3/8, and that's plus or minus 3/8 square inches. So the possible propagated error in the area is plus or minus 3/8 square inches. And that would be an approximation. It should say that the possible propagated error in the area is approximately plus or minus 3/8 square inches. The measurement of the edge of a cube is found to be 12 inches with a possible error of 3/100 inch. Use differentials to approximate the maximum possible propagated error in computing the volume of the cube. Notice how similar this problem is to the one before, and we're going to approach the solution in a very similar way. The edge of the cube is 12 inches, the maximum error plus or minus 3/100 inch. Now we understand that this error is the delta x or the dx, and they are the exact same amount in our problems. The general idea in calculating a differential for a general function y equals f of x is the differential in y is f prime of x dx. Now our specific problem, however, has to do with volume, and and volume is calculated as the length of a side cubed. Now, applying that idea to our problem, you see, applying our formula to the general form of the idea of differential, we would be talking here about the differential in volume equals v prime dx. Now, v prime, well, v prime is 3x squared, so we just pop that information into our relationship. The v prime is the 3x squared, and the dx from above is plus or minus 3/100 of an inch. Now, the value of x is given at the top of the screen is 12 inches. So making the calculation, we find dV, the differential of volume, to be plus or minus 12.96 cubic inches. So we say then that the maximum possible propagated error in the volume is plus or minus 12.96 cubic inches. Let's also find something else in this problem. Let's calculate relative error. We're going to take the differential in volume and divide by the volume itself. And for this problem, it's relatively easy. The dV that we found is plus or minus 12.96. Now the volume is calculated as x cubed, and we were given the value of x to be 12. So that relative error then turns out to be this, and as a percent, the relative error, or the percent error, is 0.75%. The measurement of the circumference of a circle is found to be 56 centimeters. The possible error in measuring the circumference is 1.2 centimeter. Approximate the percent error in computing the area of the circle. Now, in order to find percent error, we need to find relative error. In order to calculate relative error, we need to find propagated error. So we first want to find propagated error involved in this problem. We'll start the same way that we have in the last couple of problems, and this problem is worked in very much the same way, except there's a little kick involved in this problem, and I'll tell you when we get to it. The circumference here is 56 centimeters. The error is plus or minus 1.2 centimeter, and that, of course, is a delta value, and since we're talking about an error in or a differential involving circumference, it's a delta C or a DC. Now, we want to find the percent error in computing area. So we're going to be talking about an area formula. Now, the template that we start with, though, is the general idea that for a general function, the differential of y is f prime x dx. All right, now we're going to put this idea into it, the area idea. Area is generally thought to be pi r squared. So using that idea, now notice that this is area as a function of radius. So the differential of area is the derivative of area, or a prime, times differential of radius, you see. Now, here's where the kicker comes in. We have differential of radius that is being requested in our formula. However, up at the top, we have a differential in circumference. And so we can't just plug that in as we have been able to in the past. What we need to do is write the area as a function of circumference. And then we'll have differential of area is a prime dc. You see, so here's the need for writing the area as a function of circumference. Turns out that that's not too difficult. Circumference is 2 pi r. Solving for r, we can write r as c over 2 pi. So we replace c over 2 pi for the r in the other equation, and we get this, and then we can clean it up a little bit, and we can find a prime. All right, now with a prime, we just pop that information into our relationship to the left. 1 over 2 pi times c. And now the dc is the plus or minus 1.2 from above. The value of c is given, for the circumference you see, is given at the top as 56 centimeters. So when we replace it with 56 centimeters and punch our calculator, we find the differential of the area to be plus or minus 10.7 square centimeters. Now, relative error we know to be dA over A. You see that the next thing we do is do relative error and then percent error. The dA we've just discovered. The area we need to calculate. Area is calculated using this relationship. And let's see, the C value is 56. So again, punching the calculator, we find that A to be approximately 249.55. Now notice that at the bottom of the screen we have two approximations. And those two approximations are used to calculate relative error. So the dA numerator, the differential of area, is the 10.7, and the denominator, the area, is 249.55. And we find then that the relative area error is approximately this long decimal. I do want to tell you though that you get a little bit different value if you use more exact values for the dA and for the A. That is, if we made the calculation like this, and on the calculator it's not too difficult to do. You see, if we carry out the calculation for many more decimal places, then once we make the calculation we find it to be this. But these are equal to 4 decimal places, and that's really all the accuracy that we want. I just want you to realize that when you use approximations and make calculations with approximations, you sometimes end up with a small error. At any rate, the percent error is approximately 4.2857%. Or the percent error in computing the area of the circle is approximately 4.3%. It's important to remember that the delta x is the same as the differential of x, but delta y is not quite the same as the differential of y. They are approximately equal to one another. And it's also important to realize this relationship between derivative and differential. They don't mean quite the same thing, but there is this relationship because of the notation involved in both of them. That given y equals f of x, the derivative, you see, of y with respect to x is f prime of x, and from that we can sort of multiply through by dx and get this. Now, we're thinking of multiplying through, but these are not the same thing. They don't mean the same thing, but the notation is set up so that there is this relationship. And incidentally, the f prime of x is sometimes listed as y prime, and this, therefore, could be listed as y prime dx. Okay, let's continue that idea. Let's stay on that theme just a little bit, this relationship between derivative and differential. You see, if we have functions u and v, then the derivative of their product by the product rule is u times the derivative of v plus v times the derivative of u. Now think about v prime as dv over dx, and u prime is du over dx. That's the derivative of u with respect to x. Now just in terms of the notation here, if we just use the notation and algebraically manipulate the notation, we have these dx's in the denominators, so we can multiply throughout by dx, they would cancel, and we would have duv, and then these items. And now we're all of a sudden, we're in this differential world. The differential of the product is the function u times the differential of v plus the function v times the differential of u. So it follows the same kind of pattern that was found when we're taking derivative. You see, the differential follows that same kind of pattern. And we can use that pattern idea to find the differential of the quotient of functions. Now, the pattern we're following is the pattern of derivative. And here's that pattern of derivative, except we're replacing the idea of derivative with the notion of differential. So remember, it was for derivative, it would be denominator function times the derivative of the numerator as the first part of the numerator. Well, here's the denominator function times the differential of the numerator, and then minus the numerator function times the, instead of the derivative, the differential of that denominator, and then all of this is over the denominator squared. Well, let's put this into action a little bit. Let's take some rather specific functions and look at them. Here I have a listing of several functions, and in this column I'm talking about derivative of those functions, and over here the differential. And I know I'm kind of beating this subject to death a little bit, but I think it's important that we realize that there's such a cohesive kind of relationship between derivative and differential. Even though they mean somewhat different things, the relationship is according to the notation. So here we have, let's see, y equals 2x cubed, and y prime, or we can designate it as the derivative of y with respect to x, is 6x squared. And then the differential follows directly from this. It is the differential of y is 6x squared times the differential of x, or dx. And then over here for 5 sine x, the derivative is 5 cosine x, and we can designate it like this. And for differential, the differential of y is 5 cosine x dx. And then for something a little more complicated like this one, if this is our function, now notice we're going to use our product rule. And so we would have, let's see, we'd have this times the derivative of that, and then that times the derivative of this. So it is 5x cubed times the derivative of cosine x is minus sine x, and then we have cosine x, the other factor, times the derivative of the 5x cubed, which is 15x squared. And now we clean it up a little bit and we have this as the derivative. And if the derivative is designated as dy over dx, then it's pretty easy to go to the differential, and I've put the differential right here just so we can see the stark similarity between the two. It's dy equals all of this times dx, and that's all there is to it. Well, let's go through a function and let's find its differential. We can very quickly go through the process like this. If this is our function, then we might lay a pattern for what we're going to do, that the differential of y is y prime dx. And now go through the y prime idea. Well, we think about this as x squared minus 4 to the 1/2 power, and we're going to use the chain rule, so it turns out to be 1/2 times what's in the parenthesis to an exponent, which is 1/2 minus 1, or negative 1/2 times the derivative of the x squared, which is 2x. And all of this is just times dx. And then cleaning up a little bit, the negative 1/2 throws this to the denominator, and we have a radical. The 2's here cancel, so we have x over the square root of x squared minus 4, and the dx is tacked on. The period of a pendulum is given by t equals 2 pi times the square root of L over g, where L is the length of the pendulum in feet, g is the acceleration due to gravity, and t is the time in seconds. Now, before we even go on with this problem, I'd like for us to understand the nature of this formula and how it relates to a real pendulum. G now, the acceleration due to gravity, is just a constant in the problem. So the only variables are t, the time in seconds, and L, the length of the pendulum in feet. And the period is the value t, is that time. Now here's an illustration of the situation. Suppose we have a pendulum and it has a certain length. Well, the swing here is what the period is all about, and the time required for that swing is calculated according to this formula. So if we assign a value to the length of the pendulum, and let's say that that value is 5 feet, then we can replace 5 in the formula and we can make the calculation for the period, the time it takes for that swing to occur. And that time is 2.5 seconds. So that means then that this amount of time is 2.5 seconds. Now let's see what happens if we change things a little bit. Suppose we double the length. We make the length 10 feet. Are we going to double the time? Well, certainly not here, but let's make the calculation for the time involved with a pendulum whose length is 10 feet. We would replace 5 with 10, make the calculation, and we find that the time is, instead of 2.5 seconds, it's 3.5 seconds. So we increase the time by just 1 second by doubling the length. So it means here then that the time for the whole swing of the pendulum, this amount of time, is 3.5 seconds, and that's what the problem is all about. Well, let's return to the situation. Now, we already read the first part of the problem. Let's continue at the bottom. It says, suppose that the pendulum has been subjected to an increase in temperature such that the length has been increased by 0.5%. That's an interesting nuance in this kind of problem. We haven't seen this kind of twist in the problem before. So we're talking about an increase in the length by 0.5%. Let's analyze the situation. Now, here's our formula, and the length is increased by 0.5%. Now, what does that have to do with? Well, it's a percent error, you see. It's a percent error in the length, and that's related to the relative error. The percent error is just the relative error expressed as a percent. Now, relative error, we understand something about that. Relative error, when we're talking about length, would be the dl over L, the differential of length over or divided by the overall length. And let's make a note of that in this problem and go on with a question. Find the approximate percent change in the period. The approximate percent change in the period. Now, that's nothing more than a relative error having to do with the period. Now, the period, remember, is a time. So we're thinking then about a dt over t, a differential of time over the overall time involved in the problem. Now, we would begin with the idea of a differential. Now, the general idea in our general template is dy equals f prime of x dx. All right, we understand that, but how does it apply in the problem that we have before us? Well, here is our formula, and you know, maybe we forget how to take our formula and put it into the format of differential. Well, if we forget that, we can do something like this. We can think, well, the derivative of t, or t prime, is just the derivative of t with respect to L, because after all, the function here is t as a function of L. So when we talk about derivative, it's the derivative of t with respect to L. So it's dt over dl. Now, using this notation, we can kind of solve the notation to give us a differential kind of expression. Now, there's not a direct transfer in the two ideas, as we mentioned before, but it does give us an idea of the manipulation, where the manipulation can help us put our problem into the format that we desire. And so here's what we want in terms of differential. Now, let's go through and make a calculation here. We would rewrite t in this form probably for differentiation purposes, and then we would use the chain rule to find t prime. So now remember, we're thinking of this, the L over G in parentheses as a single entity. So we want to take the derivative of this t expression, thinking of L over G as a single entity, and then we'll multiply by the derivative of the single entity. So it turns out to be 2 pi times the exponent times single entity to an exponent that is 1 less than the exponent we started with. And then we're going to multiply times the derivative of the single entity. Well, the L over G is the single entity that I'm talking about, and it's a little easier to make the calculation of derivative sort of separating out our constant, because after all, the derivative of 1 over G times L is just 1 over G. So we have this, and now we just want to clean it up. The 2's go out, and we can rewrite like this. Now, we'd probably put it back into this form, the single entity, the in parentheses, is L over G. But let's just stop right here and think about what we have. Now, for the purposes of this expression, we already have t prime. Now let's just bring down the dl and now realize what we're looking for. We're looking for dt over t. We have the dt expression here. Now let's go ahead and divide on both sides by t. You see, we divide on the left by t, and on the right we have an expression for t, and that's this expression. And now really all we have to do is clean up the situation. So the pi's go out, and now the negative exponent in the numerator kicks that base down to the denominator, and L over G to the 1/2 a couple of times gives L over G, and now we can express both numerator and denominator as single fractions like this. Now this is dl over G divided by 2L over G, or dl over G times G over 2L. And the G's can go out. See, all of this is just algebraic manipulation. And now we can kind of separate out the 2 in the denominator. We kind of want to separate it out and think of this as 1/2 times dl over L. The reason we want to do that is because we have a value of dl over L here at the top of the screen, and it's 1/2%, which is 0.005. Now we can make the calculation rather easily that dt over t is 0.0025. So the approximate percent change in the period is 0.25%. Let's make another calculation. Suppose we want to find the approximate error in this pendulum clock in 1 day. Well, gee, there are several ways of making the calculation, but we could reason through it like this if we want to. We can think, well, gee, this percent change in the period is 0.25% for every second, 0.25% per second. And so all we need to do is take the relative error per second and multiply times the seconds per day. Well, what is seconds per day? Well, there are 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day. So it's 60 times 24 for the number of seconds per day. And all we need to do then is multiply that percent change in the period times the seconds per day. So we would have this, and that gives us 216 seconds, or 3.6 minutes. And therefore the approximate error in the pendulum clock is 3.6 minutes per day. Here's a rather interesting calculation that used to be very necessary and handy before calculators came on the scene. It says use differentials to approximate the value of the cube root of 28. Compare your answer with that of a calculator. Well, let's talk about the nature of the problem before we go through the actual calculation. Suppose we think of the expression as a function. That is, f of x is the cube root of x. You see, and the x is going to be replaced with 28, but we're going to work some manipulation on it here. So we think of the situation in terms of a function. Now, we know that the cube root of 27 is 3. That is, we know that f of 27 is 3. We want to find the value of f of 28. Now, we can think of the situation like this, that f of 28 is f of 27 plus 1. It makes some sense, or it should make some sense, that this is approximately equal to f of 27 plus some differential in y. Now, I'm saying it that way because f of 27 is really a y value. You know that f of 27 is 3. Well, for an x of 27, the y value is 3. So the vertical distance 3, you see, a y value is associated with that x of 27. Now, f of 28 would be a little bit different from that vertically. There is a difference in y there that will get us to the position of f of 28. And that's why that dy is there. That dy is a differential in y that's associated with the 1. Now, a little more generally, it's this, that f of x plus delta x is approximately f of x plus a differential in y, and that differential is related to the delta x. All right, let's go through a calculation. This then is f of x plus, now the dy, the differential of y, is f prime of x dx. We've seen that a number of times before. Now, the cube root of x is what we're talking about here for f of x, and f prime of x is 1/3 x to the negative 2/3. We're thinking of the cube root of x as x to the 1/3, so the derivative is 1/3 x to the negative 2/3. All right, that's 1 over 3 times the cube root of x squared, and all of this is multiplied times dx. Well, let's replace the x's here with the 27, and we get this. The dx is 1, so we have this, and now it's just a calculator punch. 3 plus 1 over 27 is 3.0370 approximately. Using the calculator, we would make the calculation as 3.0366. You see a very close approximation using differentials here. And once again, think about what would have had to have been done in the days prior to the calculator. This process was used quite often in those times to make such a calculation.